everybody. Welcome, welcome, welcome. I am assuming that we are live. I saw a go live in the middle of the countdown, so we might have been live, and I might have been staring at my camera like an idiot for about 20 seconds, but I assume we'll go live now. Welcome, everybody, to the workshop on advanced RAG techniques. My name is Zain, and I've planned this out to be about 40 minutes of talking, presenting, looking at code, and then some Q&A. There's a bunch of interest from the community around this, so I'm hoping that we can also take some questions. Um, I've also got Sebastian in the chat who's helping answer questions. So if you have any RAG specific questions, if you're building cool things, you want questions answered, or if you have any details that you want to go into with the slides, feel free to drop those in the chat and we'll take those as they come, okay? So let me dive right in. So let me change the layout here. Let me zoom into uh, the presentation. So yeah, like I mentioned, my name is Zain. I work at Weaviate. My background is in engineering and machine learning. I work as a developer advocate. A lot of what I enjoy doing at Weaviate is helping people, helping engineers, helping data scientists, helping you guys build the apps that you want to build with technologies like vector databases, language models, using them in pipelines. So I'm really excited about this workshop talk, where essentially what I did is I took a bunch of different sources, blog posts, papers, different tools, and I bunched them together into a 1 hour session where I go over everything RAG related and I talk about new techniques that you might be able to take advantage of. Um, and so this is an accumulation of about 2-3 months worth of kind of scrounging different blog posts and papers and putting together a resource that hopefully you'll find useful. Right, so let's see if the clicker is working. Right, awesome. So before we start off, at Weaviate, we're all about open source. It's core to our identity. And so keeping with that identity, everything in this talk is open source. The slides will be sent out afterwards. Every single concept that I talk about as well is open source. And if you look at the bottom of every slide, there will be a source that will take you to the to where that concept came from, right? Whether that's a paper or a blog post or a GitHub repo. So just be on the lookout for that. A lot of what I'm going to talk about will be linked to, and then you can dive into the details to see if you actually want to implement it in your own RAG pipeline. All right, awesome. So let's get started. So RAG is a kind of a general purpose framework, but to tell a better story, what I'm going to do is ground the entire workshop in an example, and that example is of the average human doctor. And so if you think about an average human doctor, in North America, they study for at least 7+ years after undergrad, right? So that's 4 plus at least 7 years. And then there's a whole residency program. So there's a whole kind of a decade plus worth of schooling that goes into becoming a doctor. And once they start practicing, they see about 100,000 patients in their lifetime, right? So the next time you go to see your doctor, effectively what they're doing is they're reasoning over their 10+ years worth of knowledge, and they're effectively kind of retrieving from and searching over experience from 100,000 patients to see which of those patients are relevant to you and what they could have learned from that patient and apply for your particular case. So in our case, what we want to do is we want to build a RAG chatbot that can help us assist doctors in their task, right? So we want to build an AI-powered medical doctor or assistant. And this is going to help us because we'll be able to break down some of the functionalities of our RAG chatbot if we think about it this way. So the first thing that we need to do is encode some of this knowledge base, right? So from a doctor's 10+ years of schooling plus 100,000 patients of experience, all of that needs to be encoded into some form of knowledge base that they can search over from. So the RAG chatbot needs to have a similar or larger knowledge base. It needs to be able to efficiently search over this knowledge base, right? So the minute the patient walks in, start telling you about their problems, in real time, you need to be able to search over that repository and say, these are the 5 patients and maybe 5 medical literature articles that might be relevant in helping address this patient's issues. It has to be able to reason. So reason is a kind of a loaded term here. Um, human doctors reason over their experience and their knowledge. When it comes to language models, when it comes to RAG chatbots, we can say that it can pay attention to the stuff that you feed into it, and it can pay attention to different components of what it's been trained on, right? So you can use the word reasoning, you can use the word attention, whatever you'd like, right? But essentially what I mean is it needs to take in data, and then it needs to be able to formulate coherent responses that are grounded in the data that you gave it. One thing that's unique to this particular application, and for a lot of regulated applications, this will be true. So this is true for finance as well. It's not just good enough to give the right answer. You have to give the right answer for the right reasons. So whatever you build, it has to be explainable. If you tell a patient that they need to have a test done, or you prescribe something to a patient, or the RAG chatbot does it, it needs to be able to explain why it's doing this, right? And this is what a doctor does as well. So explainability is pretty important. This is one of the things that RAG gives us as well. So I'll dive into this in more detail. And the last thing here, which is super important, kind of circles everything out, is all of these steps that we're talking about here, they need to be real time. So you can't kind of do it offline. The patient comes into your clinic and then you say, okay, come back tomorrow. I'll tell you what to do next. It has to be then and there, right? So anything that we build has to be performant and it has to be real time. So with this example, every technique that I talk about to add to your RAG pipeline is going to be grounded in this kind of use case. So the simplest way that you can solve this problem is simply take the patient's information, hand it off to a language model, literally copy paste it into a language model, and get it to generate some sort of answer. Right? Whether that's a prescription, whether that's a test, or any sort of diagnosis, this is the easiest thing, right? And this is typically how we use language models, where we just write into ChatGPT and it gives us some answer. Right? If you now integrate a knowledge base in here, you're starting to have the beginnings of a RAG framework. And so typically here, we're going to have some sort of information. This can be medical practice information. We'll go into the details of exactly the data set that I used, but this can either be patient cases or medical literature. And typically we'll ingest this into a database. Here I've got the word vector database. This doesn't actually need to be a vector database strictly. This can be any type of database, but I'll talk about why for a RAG setup, you would prefer this to be a vector database. And then we need to connect up this workflow into our knowledge base, right? So typically what we do is we can take this patient information and we can formulate a query to the database. And the point of this query is to extract out relevant information from this knowledge base, right? So this knowledge base might be billions of documents, but this response needs to be 5 to 10 relevant pieces of information to this patient. And then we can wrap that information into some sort of prompt template and then inject it into the language model. And then the language model now generates. And so this is your typical RAG workflow. And so if we round it out, I'm going to break this up into 3 pieces because this will inform our strategies going forward, right? We've got the indexing phase. This is where you're going to take your entire knowledge base and you're going to ingest it into some database. So here we're going to talk about chunking and other things that you can use to improve this. The next phase is the retrieval phase, where you have to efficiently search over your knowledge base and find out which 5 to 10 things are relevant, and then everything else becomes irrelevant for your particular query. And then you have the generation phase. So I call this the RAG doctor approach, because you've got the 3 components of RAG in here. And so typically when you've got your RAG pipeline and something breaks, you don't just say that my RAG is not working. You say that what you should do is the retrieval pipeline in my RAG approach is not working, or I can index my data better, or the language model is not generating high quality outputs. Right? So because RAG is a framework, you need to be more specific and eval every single component of this pipeline. And for this reason, I'm going to go into every single one of these components and talk about how you can improve indexing. How can you do better indexing? How can you improve retrieval? How can you improve generation? So on and so forth. Okay, awesome. So with that said, let's dive in. Right? So in our case, because I want to make everything pretty concrete, the data set that I used for this workshop is called the PMC patients data set, and this is an open source data set where they collected information about patients and medical literature. And if you go to this is a Hugging Face link. They've actually also embedded and vectorized this data set, so it's really easy to use with a vector database. Just to provide a quick summary of this data set, it has about 170,000 patient summaries. A patient summary is you walking into the doctor's clinic, telling the doctor about your problems, the doctor giving you next steps, and then eventually the diagnosis, right? So you can think of it as a one pager of a patient interacting with a doctor, and then all of those are different kind of interactions. And then it also has about 1.4 million abstracts from medical literature. And so I've taken all this data, I've indexed it, and this becomes the kind of the knowledge base that my RAG chatbot will be able to retrieve from. For now, this is only text data, but you can also think about indexing in images, charts. So typically how you want to do that is take some sort of language vision model, get it to describe the image, and then that image description becomes the chunk that you can retrieve and then reason over. You can do a similar thing for charts as well. And the great thing about this data set is that it's actually a retrieval benchmark data set. And what that means is you have the ground truth retrieval results from this. So if you have a patient, the data set tells you these are the 5 ground truth patients that are the most similar to this one patient. And so when you're setting up your RAG pipeline, you can actually use the ground truth from this data set to evaluate how well your pipeline is working versus the ground truth. And so each one of these components can have an eval component. And so when I was building this out, I kept this in mind, and this is one of the main reasons why I picked this data set over another open data set that I could have chosen. So if you look into the paper where they published this data set, they break it down into these 2 components where you've got PubMed literature articles, so you can retrieve relevant articles, but then you also have similar patients that you can retrieve from as well. And this is a live database, so they keep on updating it. So last time I checked, it was 1.4 million articles and 167,000 patients, but they keep on updating it as they get more information. So this is going to be our data set. And the use of a vector database here, I mentioned that I'd come back to it later. The reason why you would want to use a vector database here is typically when you've got a RAG setup, you've got a language model that kind of excels in language. You want to couple it with a knowledge base or a database that can be queried using natural language. So typically here, the query is a natural language query. And the vector database scales up your vector search up to billions of objects, right? So you can keep on ingesting in data real time into this, and then a patient query can come in and you can retrieve only the relevant components to that. Right? So for this application, I used Weaviate, which scales up to billions of objects, and it also allows you to do multi-vector retrieval, right? Which was particularly useful for this application, as I'll show you in a second. So typically the use of the vector database is to narrow down from this kind of billions of documents down to the 5 that are relevant for your application. And so typically the patient would come in, they would tell you something like this, right? So my left shoulder hurts and I have numbness in my thumb and index finger. You pass that in as a query to your vector database, and a vector database essentially, you can think of it as a vector space of objects that are close together and further apart depending on semantic similarity. And the vector database then tells you these are the objects that are the most relevant to this query. And in my case, what I did is I set up a multi-vector system where I've got patients that I can retrieve from. So here, these are the 3 most relevant patients. And then these are the 3 most relevant article IDs to this particular patient. And now the advantage here is that I can tell the language model, you have to solve this patient's problem. These are cases that might be relevant for you to read, and these are medical literature articles that might be relevant for you to read as well. And so this is the problem that the vector database is going to solve for us in our basic RAG setup. All right. Okay, so the main question of this workshop that I'll spend the next maybe 30, 40 minutes talking about is how do we take this basic RAG setup, this kind of retrieval and then generation, and how do we improve on it? Right? What are some components that we can introduce into each one of those phases, the indexing, the retrieval, and the generation phase, to up our game here. And so we've only got 1 hour here. So the point of this workshop is not to make everybody RAG experts. I don't claim to be a RAG expert either. But the point is, if you've got a RAG pipeline and the retrieval is not working, or you think you can index data better, it's to introduce you to topics and techniques where you could say, oh, that might work really well for my application, and give you the resources that can be jumping off points into that resource, and that can kind of set you off on an exploration phase to maybe take another chunking strategy and introduce it into your pipeline, and your pipeline is all the better for it. Okay, so we're going to start off at the beginning, indexing. So you've got kind of millions and billions of objects, or you've got huge PDFs. The first thing that you start off with is indexing. So how do you do better indexing? So this starts off with text, chunking text. And typically the idea behind chunking text is we want to have semantically coherent pieces of information, right? So if you've got if you've got a document, there's multiple concepts that are being covered. You can have one kind of train of thought, and then topic switches. You start talking about another thing in another paragraph. You want to chunk that one piece of text, which is about kind of one semantical concept, and you want one vector to be generated from that chunk. The reason why this is not easy and this is not a solved problem is because if you choose chunks that are too big, you can have different topics being covered in the same chunk, and now the vector is some average of all of the topics that are being covered. And on the other end, if you choose a chunk that's too small, then what happens is there's not enough meaning in that, right? So just imagine if the chunk is only 2 words here, chunks 2, you can't really extract any semantic meaning from 2 words, right? So if your chunks are too big or too small, it's no good, right? So you need some kind of sweet spot in between. You can think of this as some form of hyperparameter tuning, where your chunk size is a hyperparameter and you need to find the best size. This is a really good blog post from Stack Overflow that goes into this, defining why chunking and the chunk size is not really an easy problem to solve. So typically the easiest way to do this is by doing a fixed size chunk, right? You've got your text, and then you say, I'm just going to specify a certain character size, let's say 35 characters, and I'm just going to count up to 35, create a chunk. Count up to 35, create a chunk. One interesting thing that you have that you'll notice here is that you've also got an overlap. So typically when you're chunking, you've got kind of a train of thought that's going on, and then you don't want to abruptly end it. So what we do to take that into account is we'll take a window before and after, and we'll include it in the previous chunk and the coming up chunk as well, so that if there's meaning that needs to be transferred from one chunk to the next, you get this overlap, which will allow you to kind of connect the 2 chunks together, so that there isn't just like a drop off and then the next chunk kind of is disconnected from the previous chunk. The problem with this approach is that it doesn't respect the structure of your document at all, right? It's literally just counting up. It's a counter that kind of terminates and then it starts counting up again. So you could chunk anything with this, but it's very generic and it doesn't respect the structure of your document at all. Another thing that you can do here is called the recursive character text splitter. Typically, when I talk to people, this is the strategy that they're using. And this is good because it respects the structure of your document. Right? Here, you can choose to chunk on new line characters or paragraphs, and then what you'll get is a dynamic chunk size that respects the structure of your document. So here in the first kind of paragraph, 2 sentences, you get 1 chunk, and then in the next paragraph, you get the second chunk, and the third chunk is the third paragraph here. And so here you choose specific characters that you chunk before and after. And this way, this ensures that you're not cutting off a sentence in the middle, or you're not cutting off a structure right in the middle. So this is better than the previous strategy. So typically, this is what people use. An improvement on this is to do document-based chunking. And so now, depending on what you're ragging over, you might be ragging over a code base, you might be ragging over a PDF or Python code. Each one of those will have unique characters, right? So if you're ragging over HTML, you might have different paragraphs, headlines, different sections. So you might want to chunk based on those. Okay? If you're ragging over Python, you'll have class definitions, function definitions, tabbed function definitions, new line characters. You might want to chunk before and after these specific keywords. Okay? And so this is true for different documents, and this is why it's called document-based chunking. And if you look at different frameworks like Llama Index and LangChain, these will have these defined for you, and you can simply choose which type of document you want chunked, and then include the list of separators that you want to chunk on. And this will give you more kind of document-specific, domain-specific chunking, and this will work often better than the recursive character splitter because now the characters are tuned or they're specific to your particular document. And so this is a notebook that goes into this technique as well. Okay. Another form of chunking is called semantic chunking, and this is an interesting one. What you do here is you take every single sentence. So I was puzzled by the 1401, and then you take every sentence, you turn it into a vector, so you embed it, and then you compare how similar every sentence is to every other sentence. So you kind of read from top left, and you keep on reading. And if the sentences are similar enough, they belong to the same chunk. You don't start a new chunk. The minute you start off on a different topic, you create a chunk. So you kind of start off sentence by sentence, and you keep on adding to the previous chunk. And if you start deviating in meaning, meaning that the vectors are getting farther enough, then you start off a new chunk. Right? So if you do this over an entire document, this is what it looks like. And this is quite an involved graph, so let me go into it one by one. On the x-axis, you have the sentence index. So this is about 350 sentences in this document. And on the y-axis, you have your cosine distance between consecutive sentences. Right? So sentence 1 and sentence 2. And so you're going to plot this out here. Notice that the transition from chunk 0 to 1, 1 to 2, 3, always happens when you have this big peak. You have this big peak here, so on and so forth. Right? And so what's actually happening here is you can imagine reading a PDF, and in your mind, you're saying, is the author still talking about the same concept, or have they switched concepts? When they switch concepts, you say, I'm going to create a new chunk right here. So this is more of a dynamic chunking strategy where you're looking at the semantics of what's been talked about. And when the author shifts train of thoughts, you create a new chunk dynamically over there, which is why in this case you get smaller chunks and bigger chunks, and you can also get these really small chunks. So you can imagine this is some form of the author talking about one concept, and then they go off on a small tangent, and then they come back to the concept. So now you've got like 3 dynamically sized chunks that take into account this side tangent that the author went on, maybe in a side example that they're giving here. And so the cosine distance here is a hyperparameter. You can set this, you can increase or decrease this depending on your topic. And the other thing you can also do is if you have a chunk that's too big, you can recursively do semantic chunking on this with a different cosine distance to maybe chunk it up into smaller bits as well. Awesome. I'm just looking at some of the questions here to see if we want to answer something real time. I think we've got everything pretty much handled. All right, awesome. So one other thing that I want you to notice is that as we're talking about the different chunking strategies, we're kind of increasing in complexity, but we're also increasing in cost. These are all fixed chunking strategies that cost nothing. Here we're using BERT-based embedding models, so they cost a little bit more than our previous strategies. The next strategy is called language model-based chunking. Some people call this agentic chunking. And this was proposed a few months ago, where here you get a language model to chunk for you. So what you do is you give it fixed sized chunks from your PDF, and then you ask a language model, which in this case they train a language model and they call it a propositionizer. And the job of this propositionizer is to take this chunk of text and to create kind of semantically isolated sentences that can be read just by themselves, right? So this is a self-supported sentence that can be understood just by reading it. This is another one. This is another one. And so you create this factoid wiki from your own documents. And then what you do is you can go in and you can define what retrieval unit do you want. Do you want to retrieve propositions, or do you want to retrieve sentences or passages? And the language model then looks at these individual factoids and it joins them together, and it decides whether one factoid belongs in the same chunk as another factoid. Right? And it makes sentences and passages. And so then when you're retrieving, you can choose to either retrieve entire passages or combinations of proposition sentences or individual propositions. And so in this paper, they talk about which strategy to go with, whether you want to retrieve just propositions or just sentences, and kind of the experiments to help you decide when to use which. This is also a small plug. So if you're interested in keeping up with some of these strategies, weekly I'll post papers on different techniques that are being introduced. And so if you want to keep up with this, I encourage you to go to Weaviate paper reviews, and you can follow through with that. All right, awesome. So the next strategy that is really easy to use, and it gives you a lot of kind of performance in your RAG pipeline, is to just use metadata. Right? So the idea here is you want to include and get rid of chunks based on metadata, not just semantic similarity. So the example here is if you have a query that comes in, and this query is only relevant for Alice, this is your metadata, and you have some vector for this query, you don't want to match this vector with every single object you have in your database. You want to do some sort of filtering that says, because this query is for Alice, I'm not even going to look at Bob and John. I'm only going to look at Alice's data. So you filter Bob and John out, and then now you only do semantic search over Alice's documents. And these can be lots of documents as well, but you do this kind of filtering to eliminate based on metadata, and then you perform search on top of it. And so typically when you're using Weaviate, you can include the metadata filtering right into your query, where you can have a query and then you can have a filters argument where you can specify how you want to filter. And these are hard filters, and you can have as many filters as you want, so you can join the filters together. So typically when I tell people about this, their question is, well, all I have are text chunks. I don't really have metadata around the text chunks, right? So one really cool thing that I found out about recently was this model called Gliner. And so this is a general purpose named entity recognition model, which allows you to generate metadata for your text chunks as you're ingesting the text chunks. Right? So this was really interesting because with this model, what you can do is add this to your pipeline. And let's say you have a chunk of text that's coming in. You can pass it to a Gliner model, and you can say anywhere in this text is a person mentioned, is a date mentioned, is a place mentioned, and this will generate a JSON of metadata for you that you can ingest into your vector database along with the text chunk. So to give an example of this, imagine this is your text chunk on the top here. So this can be any generic text chunk. You can pass in any labels that you want here. And this is what's so robust about the Gliner model. You can choose any label. This can be kind of medicines, diagnoses, anything you want for this particular chunk. These are these labels, so person, books, locations. And the Gliner model will kind of attend to all of these tokens and these label tokens, and it will label every time it finds these particular this particular metadata in your text chunk, and it will output this JSON, and then you can ingest that in with your data. So then when you're searching for chunks that are relevant to your query, you can parse the query out and say, okay, this query is asking about a book over here, or this person is asking about this person. So now you can perform filtered search on your chunks where you've got this ingested. And the really cool thing about this is that if it doesn't find this particular label, it will just give you nothing. So there's not a lot of false positives. So the worst case scenario is that you end up ingesting a chunk and there's no metadata because it didn't find anything that was relevant for it. So this was a really interesting find, and I've been using it to add metadata to my chunks for some of the side projects that I'm working on. This model is also open source, and there's a new iteration of this model that recently came out, I think about 3 weeks ago. So you might want to look at the new and improved version of this. The reason why I included the architecture here is just to show you that this is not a GPT model. This is a BERT-based model. So it is quite small and efficient. So you can add this to your ingestion pipeline, and it won't add that much. It's not that heavy of a model. So you can simply add it to your pipeline and get it to generate metadata for you. All right. Okay, so that was our discussion about improving ingestion. So hopefully you'll have a better idea of how to chunk your data, how to use filtered search, and then how to generate uh, your own metadata if you don't have metadata that comes kind of prepped with your data. Next, I'll talk about how to do retrieval better. So retrieval is all about going through millions or billions of documents and identifying the 10 or 15 or 5 that are the most relevant, right? So it's almost like searching for a needle in a haystack, really. And so this is where a lot of RAG pipelines make it or break it, right? If you're giving the language model irrelevant information, then you're guaranteeing that it will generate irrelevant responses. You can even get it to hallucinate if your retrieved documents are irrelevant enough. Right? So you want to make sure that this part of your pipeline is working quite well. So 3 ways to improve the retrieval pipeline. The, Probably the easiest way is to use hybrid search. So the main idea behind hybrid search is that if you're working in a very specific domain, everybody here is working in a very specific domain, whether you're working in e-commerce or finance or medicine or insurance or whatever, typically your domain will have individual keywords that are kind of niche to that domain, right? So in medicine, we've got different anatomical words, we've got diagnoses, we've got disease names, we've got medication names and pharmaceutical names. There isn't really a lot of semantic matching that you can do between those domain specific names. So the idea behind hybrid search is you typically don't want to use vector search to match between medication names or different diagnoses. Two two medications might be very similar but have a very particular use case where only the doctor knows about them. So instead of getting a general purpose embedding model to differentiate between those two concepts, you want to identify that they're differently named, and you want to use the fact that you have different keywords for both of them. So what hybrid search does is it performs both the vector search and the keyword search in parallel, and then it allows you to combine them by defining some sort of fusion algorithm. And so here, the idea is to use the best of both worlds. And so typically, what you'll do is you'll take your query that the patient tells you, and you'll run an in parallel BM25 keyword search and a vector search, and then you have some form of combination of these two. Um, Depending on the vector database you're using, this could be very difficult or very easy to do. So with Weaviate, this is a simple word change. So typically this would be a near text query, but if you change this to a dot hybrid, then you're automatically just leveraging the hybrid search functionality. And the reason why this is easy is because in Weaviate, the minute you index your data, you pass it in, we're creating both the vector search index as well as the inverted index that allows you to perform keyword search. So it's as easy as just turning it off or turning it on. You can simply query it differently, and you get all of this hybrid search functionality for free. So typically what happens with hybrid search is you've got vector search that's giving you for every object a score, and you've got your keyword search, BM25 typically here, that's giving you another score, and then you have some sort of kind of fusion algorithm that combines both of these, which gives you the combined score for all of these objects. And then you've got these IDs that are associated with these, and you can take like a top 5 of this and send that to the language model to generate answers with respect to. All right, awesome. So the next thing that's really cool that you can do here is to admit that you have no idea how to talk to a vector database or a language model. Um, and so this is a very interesting thing where typically there's a whole field of prompt engineering where you learn how to prompt a language model well. And it's really easy to tell when somebody can use a language model well and when they can't use a language model well. But the other thing that I'll also add here is that there's also an art to querying vector databases, right? to giving the right pieces of information, to making a query that's not too short, not too long. It has all the semantics. It has all the keywords for your keyword search for hybrid as well. So typically, the first part is to admit we have no idea how to query these GPT or BERT-based language models properly. So what we do then is we get a language model to optimally rewrite both the query to our vector database as well as the query that goes to our language model. And so there's open source frameworks that help you do this as well. And I think Cohere just recently announced another one, their prompter model. But the idea here is we want to give our query or what we think our query should be to a language model, and that intermediary language model rewrites our query for us, and then that rewritten query is what goes to our vector database down here, or the language model that we've given up here. And so typically how this works is this is the query that the patient told you or they gave you. My left shoulder hurts and I have numbness in my thumb and index finger. You give it to some language model, and the language model says, no, 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 don't use this guy. Use this guy instead for your vector search, right? And this is harder for a human to understand, but this is more optimized for a retrieval engine so that it can retrieve better. And so typically our workflow looks like this, where we take the input from the patient, we give it to a retriever. Typically a database can be a search engine, a web search as well. You give the relevant documents to a language model, and then you get some sort of output. But with the rewriter in here, the input goes to a rewriter. The rewriter rewrites your query. So this is the input to the rewriter. This is the output from the rewriter. And then you get more relevant documents that show up here. And then you give this to your other language model, which can then generate a response for you. So this is for query rewriting for your vector database. If you look into this resource, they actually have code for this language model query rewriter as well that you can use. And then the other piece, rewriting queries for your language model. So there's different frameworks out there, but this is one of my personal favorites. DSPY is a framework that allows you to define the input and the output, a way to measure how well the prompt is working. And then it uses a language model to iteratively improve the prompt to the language model so that the performance keeps on increasing. So this is more of an optimization framework that allows you to automatically prompt engineer for a given task. And so you kind of define a task and then you set it off on this optimization process, and then it gives you the perfect query to the language model, and then you can start using that from that point on. All right. I'm just looking at the questions on the side here. All right, I think we're good to go. So if you've done all of this other stuff and still your retrieval recall is not good enough, you're still getting irrelevant results, then the last thing that you can look into is fine-tuning the embedding model. So when you're using an embedding model, you're using its ability to differentiate between topics. You're using its ability to tell the difference between something that's similar to the query and something that's dissimilar to the query and retrieve it, right? So typically people start off using general purpose embedding models, but once you've tried everything else, once you've tried hybrid search, once you've tried query rewriting and all these other techniques, another thing that you might want to do is curate your own data set and fine tune the embedding model to teach it the similarities and differences for your particular domain, right? So in this case, you might tell it the difference between two very similar medications that are slightly different. And so you can train it to differentiate between domain-specific concepts, in this case, in medicine. So what I ended up doing for this application was using a biomedical fine-tuned embedding model where it's been fine-tuned on examples from medical literature, right? And in this case, I use two different embedding models. One is for the query. This one is optimized for short text, more small questions. So I use the MedCPT query encoder to take patient information, turn that into a query vector, and then I use the MedCPT article encoder that takes in longer form articles, so entire pages, um, longer abstracts, and it encodes those using a separate embedding model. Both of these are trained in pair, so they know about each other and you can use them together, right? But they're separate models. And so both of these models are also open source. And there's a whole video that uh, JP and I recorded on how to choose your embedding models and when to fine tune, what to fine tune with, that you can also look into, that I link at the bottom here. All right. So the last piece that I'll talk about here is better generation. And my better generation is going to be biased towards choosing relevant results, right? So here, typically, you can also have a pipeline to the language model that says the language model ignores irrelevant results. And so a lot of my better generation strategies are going to be talking about ignoring irrelevant results that the vector database might be suggesting. So the first strategy that I'll talk about here is called AutoCut. And so this is something that we came up with at Weaviate. And the idea behind this is quite intuitive. So the idea here is that even with all the tips and techniques and strategies that we've talked about to improve the retrieval process, you might still get irrelevant results. And so what you want to do is look at the relevancy of those results and identify if there's big jumps in relevancy. Right? So you might say that the top three uh, patients that are retrieved are really relevant, but the fourth and fifth there's a big jump between them. And so when you look at the distance between your query and those individual retrieved results, you can automatically cut off ones that have a big jump in similarity. And so we kind of implemented this in Weaviate, and you can use this by simply passing this into the query and telling us how many kind of relevant segments do you want to encode. And the main reason to use this in your RAG workflow is to take away irrelevant results. Right. So typically, how you do this is your rewritten. Notice this is the rewritten query now, goes into the vector database. The vector database retrieves patients. So here I've only retrieved patients. I'm not retrieving over my article base for now, just to keep this example simple. You get this 6 patient cases that are retrieved that the vector database thinks are relevant. It also gives you these scores for each one of these. And the thing that I want you to notice here is that there's this big drop off in score from the 4th to the 5th and the 6th. And so what AutoCut will do is recognize this big jump. It looks at the rate of change of the similarity scores between the different documents, and then it says, hey, there's a big jump here. Maybe you don't want to include these in the generation phase, right? So don't inject this into your prompt. Only keep the top 4. Um, and so to do this, you can have an auto limit that you can set to 1, and this will have kind of one continuous piece of similarities. If you set this to 2, you'll also get the second one here as well. So this is also another hyperparameter that you can check to see how many pieces of relevant context do you want. Do you want all the patients that are similar to each other, or do you want 2 groups of patients that are similar enough? And you can set that auto limit to enable the AutoCut feature that will come into play. Right. Re-ranking is another technique that you can use. This is also very powerful, and uh, pretty much everyone that uses re-ranking benefits from it in their RAG pipeline. So the idea behind re-ranking is we've got one model that's used in the vector database to rank all of these objects based on similarity to the query. Right? Re-ranking is exactly what it's proposing. You take these ranked documents and you re-rank them, right, based on relevancy to the query. And so you could say, well, I just rank them. Why do I want to re-rank them? Or why do I want to redo this process again? Right? And the answer here is you're using a much more heavier model. You're using a much more purpose-built model that you can use to look at individual queries one at a time and kind of go through it with more of a fine-tooth comb. And so typically, the workflow here is you take your query and you overfetch. You retrieve a lot more results than are necessary. Typically, this is anywhere from 15 to 20 objects, and you might only need 5 to give to the language model, right? So I've overfetched a bunch of documents here, and I've got a similarity score based on the vector database, and this is why they're kind of ranked accordingly here. So what we do now is we ignore these scores for now. We give these documents and the query to a re-ranker model. And the re-ranker model looks at each one of these individually. So it'll look at the query and the patient case one at a time, then this one and this one, this one and this one at a time. And it says, maybe the first one isn't really that relevant, so I demote it to third rank. The third one is actually very relevant, and the vector database messed up. We want to promote it to first space here, right? First rank. And so now you get these re-rank scores, and now you can say, okay, give me the top 6 or top 5 that I give to the language model to generate off of. And so typically you would have to bring in the re-ranker module and add this to your pipeline. But because this is such a common workflow, we've already done that in Weaviate, where if you take your near text query, you can have a re-rank parameter here, and you can specify any re-rank module. This can be an open source re-rank module that you've got on Hugging Face, or this can be a re-rank module from a provider like Cohere or Gina, for example, that you can pass in here. And this will kind of add the re-ranker pipeline to your query as well. One of the things that I want to dive into here that people might have questions around is why not just always use a re-ranker? One of the reasons is because it adds latency to your RAG pipeline. So typically when you're using a vector database, you're using a bi-encoder type of setup where you've got your query that goes in, and you've got your documents that have been indexed and vectorized separately. And all you need to do at query time is vectorize the query and calculate the cosine similarity between the query and all of the other documents. And so this is pretty quick. You only vectorize one thing and you can calculate distances. And so this is typically what we do. With a re-ranker, this is more similar to what we do. We take one query and one document at a time. We concatenate them together. So you can say these are the sentence of the query, and these are the 20 sentences of the first document. You concatenate them together, and then you embed it. And so if you were using a re-ranker model that's based off of a cross encoder, which they typically are, you would be sitting there, and if you had 10,000 documents, you would be performing 10,000 forward passes through your BERT-based embedding model for every single query. And so that's not possible to keep this real time. Again, this has to be real time. The patients walked into your clinic, and you can't go offline for a day. You have to tell them some sort of answer then and there. So typically you want to use the bi-encoder to narrow down 15, 20, 25 objects or documents that are relevant. And then you use the cross encoder on top of those 15, 20, 25 documents to say which 5 are the most relevant. And you can spend the time to concatenate the query with those 15, 20 documents and pass them through your cross encoder. And the cross encoder will tell you how relevant is the query to that individual object. So this is quite a powerful tool that you can add to your RAG pipeline. And a lot of these re-ranker providers allow you to do this with one line of code. You can do this with Weaviate with one line of code to your query as well. Okay, and the absolute last thing that you can do to improve the RAG pipeline is to have multiple language models that are fine-tuned on specific performance. So if you've done all of the above things, then you can also take your general purpose language model and maybe fine tune it for your specific task. You have to be careful with this, because if you fine tune a language model for one domain, then what you're doing is you're taking all of its performance points and you're dumping it into one domain, and it'll underperform on other tasks and it'll overperform on that one task. So what you definitely don't want to do is fine tune a language model and get it to do everything. You want to fine tune the language model and use it specifically for the thing that it was fine tuned for. And so typically how this can happen is you can have one base language model and you can have different fine tunes of it that you've deployed, and then you can use those for the tasks that they're fine tuned for, right? So for this particular application, one example that I'll give you is the Meditron 70 billion, which is an open source biomedical medicine language model. And this one is pretty interesting because they do two types of fine tuning to get this. They start off with a Llama 2 70 billion. So they're not using Llama 3. This is from some time ago. So they're fine tuning Llama 2. And so they pre-train it on about 50 billion medical tokens. And so this is from the same PubMed database. So they take about 50 billion tokens, and then they just do next word, next token prediction, and they fine tune the model on this. So this is continued pre-training, but then they also do instruction tuning on it as well. Right? So they give it medical domain multiple choice questions, and then they improve its performance on the medical domain as well. And as a result, it outperforms not just its base model. So Llama 2 is the base model that Metatron was fine-tuned from, but it also outperforms uh, the GPT 3.5 model on medical reasoning tasks. It'll underperform on other tasks, but all we care about is medical reasoning. So you may also want to look at this. So one other thing that you'll notice is all of the techniques that I'm mentioning, I'm typically going from easy to implement, low cost techniques to difficult to implement, uh, kind of more offline techniques and more costlier techniques, right? So typically you want to start off with easier techniques, lower hanging fruit, see if that improves your pipeline, and then incrementally increase the complexity of the techniques that you're using to improve your RAG pipeline. All right. So yeah, so this is the RAG, this is the pipeline that they use for Metatron. Typically, people either just do supervised fine tuning, instruction tuning, or they'll. So this is the more common one. So if you go to Hugging Face or some of these other training fine tuning libraries, they'll give you the ability to fine tune using supervised fine tuning or instruction tuning. Okay, so all in all, this is the high level overview of your RAG pipeline. And we broke it down into indexing. We talked about how different chunking techniques. We talked about using metadata to filter your chunks. This is a very low effort, high return on investment strategy. And then you can also generate your own metadata. Talked about retrieval, how you can use hybrid search instead of pure vector search or pure keyword search to get the best of both worlds. We talked about rewriting the query that goes to the language model and the vector database. So two query rewritings in there, not just one. And then eventually fine tuning the embedding model when you've got your own data set curated. And then we talked about how to further remove irrelevant things that go into the language model. So rather than just injecting whatever comes out from your retrieval phase, you also have this kind of additional phases of relevancy checking before you inject it into the prompt and give it to the language model to generate with. These are a bunch of resources. So a lot of this talk is kind of pieced together from different resources, but these are a couple of surveys on RAG that I would recommend for people to look into. There's also a three-parter from O'Reilly that's really, really great. I recommend people look into this if you're interested in it. Another thing that we're starting off is in our Slack community. We're starting off, and there's a channel that you can join. I invite you to join now. It's called the RAG Corner, and there I'll be there every day. We've got Eddie, who's the creator of Verba, who's going to be there as well. And if you have kind of specific questions about chunking strategies or whether you should fine tune your embedding model or not, how to best use hybrid search, what alpha, how much keyword, how much vector search to keep in for your pipeline. This is where you can ask questions. We can have discussions. If there's any new techniques that come out that I find out about, I'll be posting it there as well. So I invite you to join. This QR code will take you there. Another thing that I'll also kind of talk about here is our open source RAG application. So we've been building this for a while, and this is led by our developer growth team, kind of spearheaded by Philip and Edward. And so there's a lot of things that we talked about here. If you want to keep up with a lot of them, I would recommend looking into Verba. Verba is a kind of a custom-built RAG application that implements a lot of these tips and tricks for you. It's also open source. So one thing that I want to show you here is if you go to Verba Weaviate.io, we've ingested all of our documentation and all of our kind of blog posts and transcripts and everything. So you can ask it how to use Weaviate. But the more interesting piece here is that it's fully open source. A lot of people are using it to build their own RAG apps on top of. And the reason why I'm pointing you to this resource is because if you scroll down here, it's a kind of a living, breathing resource where we're implementing lots and lots of really cool bits and pieces here, right? So it'll be multimodal in a while. This is a planned update that Edward is working on. Filtered search, advanced querying, re-ranking. These are all things that I talked about in the workshop, and they will be in Verba coming up as well, right? So if you want a tool that implements a lot of what we're talking about, this is your perfect go-to tool, right? So I would fork this and build with Verba. And so this, I just put in a QR code here that takes you to that GitHub repo. And I'll send out these slides later as well. I'll share them in the Rag Corner Slack channel. So for people that join, you can have access to this. We've also got a webinar that's coming up. So one thing that I didn't go into, which is kind of a side topic, not relevant for this talk, but it's about scalability and performance, right? So when you're using a vector database, typically you fall into different buckets where you might require the fastest throughput. You need to have the lowest latency, and you're willing to pay for that kind of fast throughput, really fast querying. Or you might want a lower cost option where it's okay to have a higher latency, lower throughput. And so for that, we're introducing new and improved kind of features. And if you're interested in this idea of kind of tying cost with different tiers of storage, whether it's RAM or whether it's cloud storage like an S3 bucket, we're going to do a deep dive into these techniques in a webinar that's coming up next month. So I invite you to sign up for that as well. This will be led by Sebastian, and Etienne is going to be there as well, our CTO. So you can bring all of your questions about scaling vector databases up to that webinar. And then the last thing here is just thank you everybody for being here. So I know there was a lot of interest from the community around this. If you have suggestions on how we can improve this and what we can do to serve you guys better, let us know. These are all of our community handles. If you have questions for me, feel free to connect with me as well. One thing that I'm doing right now is taking this workshop and I'm breaking this down into kind of uh, deeper 1 hour sessions on every single component that we talked about. So we're going to have a 1 hour deep dive into just chunking, 1 hour deep dive into just retrieval, 1 hour deep dive into just generation. And so if you're interested in that, follow our community page, and we do workshops weekly that are live as well. So um, you can follow us, and you'll get updates. And I hope to see you in another workshop soon. Thanks, everybody.